So I present a combination of the dual spectroscopy of angular interrogation surface plasmon resonance. Go to background. The surface plasmon resonance, or SPR, is a representative optical sensor of refractive index. In SPR, so when a monochromatic laser light is incident into the glass prism covered with a thin metal film near the total reflection angle, the induced evanescent wave is coupled with the collective vibration of free electron, namely surface plasma. So this results in the conversion of light energy into the surface plasmon energy. So we measure a reflectance spectrum with respect to the incident angle, the reflectance largely increase near the resonance angle, namely theta SPL. So this is angular SPL dip or SPL dip. So this SPL dip is very sensitive to the refractive index near the sensor surface via the electric field caused by the surface plasma. So we can achieve the precise sensing of refractive index by measuring the spectral shift of SPR dip like here. Furthermore, so if we made the surface modification of antibody on the sensor surface, like here, antigen-antibody interaction change the effective RI near the sensor surface. So in this case, the SPL can work as an optical biosensor. So in this way, the SPR has a future of the high sensitivity, cost effectiveness, versatility, ease of testing, and point of care prospect. However, there are still key challenge. So the conventional prism rotation is too slow for the real-time sensing. Only the angular intensity spectrum or SPR is observed, and the limited resolution for the precise RI sensing. So to address this key challenge, we focus on the optical frequency comb or OFC as a new way to read out the spectral RI-dependent spectral shift of SPL dip more precisely. Next slide shows the concept of OFC-based angular metrology via the spectral to angular mapping. So the OFC is composed of a series of frequency spikes regularly separated by a constant frequency like here in optical amplitude and phase. And the OFC possesses both characteristics of the narrow line width and the broad spectral coverage together with a constant frequency spacing. Most importantly, the uncertainty of the optical frequency in all OFC mode is secured by an electric frequency standard via the laser control. Therefore, OFC can work as an optical frequency ruler secured by the electric frequency standard. Next, we consider that the OFC is incident into a diffraction grating. So in this case, each OFC mode is separated at a different angle depending on the wavelength. In other words, angular dispersion is given by a function of lambda. So such a angular dispersed OFC mode can work as an optical angular scale with having a dual scale of optical amplitude and phase. So key point of this optical angular scale is like here. So the first wavelength and the angle of each OFC mode are one-to-one matched. Second, each angular tick has a frequency standard level accuracy. And third, the dual scale of amplitude and phase gives a complex angular spectrum of the SPL dip. Next slide shows the comparison between the conventional SPR and the OFC-based SPR with wavelength spectral to angular mapping or lambda to theta mapping. In the conventional SPR, the mechanical rotation of the prism is required, which limits high-speed measurement. Also, only the intensity-based reflectance spectrum can be measured, but limiting the amount of information and sensitivity. Conversely, the proposed method is based on the dual-com spectroscopy of angular SPR spectrum using lambda to theta mapping OFC. So such an approach does not need the mechanical scanning, so enabling the real-time measurement possible. Also, the simultaneous acquisition of optical amplitude and phase spectra with a high resolution and high accuracy can be used for the measurement of complex angular spectrum of SPR deep. So to this end, so there are two keys. The first key is the lambda to theta mapping OFC with a grating. So when the OFC is incident onto the diffraction grating, like here, each OFC mode is angularly dispersed according to the wavelengths, following this diffraction equation. In other words, wavelength angle conversion can be achieved in the OFC. So the important is a one-to-one mapping between the wavelengths and angle is established. So in this way, the wavelength domain OFC can be converted into the angle domain OFC. The second key is the dual-com spectroscopy or DCS. So here, upper shows a typical configuration of DCS and the principle of measurement, respectively. But here I skip the detailed explanation. Inversely, I give the key point of DCS like here. So the replica of OFC is generated and measured in the RF domain. So this enables a real-time, high-resolution, and high-accuracy measurement, as well as a simultaneous retrieval of the optical amplitude and phase spectra as a complex spectra. Next slide shows the experimental setup. Here we use a pair of fiber OFC at the 1.5 micrometer. One is a signal OFC and the other is a local OFC. The frequency spacing or f-rep of both OFC is around 100 megahertz, and the frequency difference between them or delta f-rep was set to be 320 hertz. The signal OFC is incident onto a grating for the lambda to theta mapping. With a combination of the grating and a relay lens system, each OFC mode is incident into the glass prism at a different angle, like simultaneously, like here. And then the reflected light it can pass through another combination of a relay lens and grating. As a result, the spatially separated each OFC mode is combined again. So in this way, the signal OFC can work as first the wavelength ruler, and then the angular ruler, and finally the wavelength ruler again. The resulting OFC, signal OFC is interfere with the local OFC for the zero-com spectroscopy. Finally, so the replica of angular SPL deep can be read out as an RF spectrum like here. So this angular to spectral to angular mapping system has an angular resolution of 0.38 milliradian, and the corresponding optical frequency resolution was 49.2 gigahertz. Before performing the telecom spectroscopy, we use an optical spectrum analyzer to check the SPR deep and its RI-dependent shift with lambda to theta mapping OFC. The top left shows the experimental result of reflectance spectrum with respect to the incident angle and corresponding wavelengths. So we confirm the spectral dip appears around 72 degrees, And such a deep shows RI-dependent shift like here. So in this experiment, we use a water ethanol mixture with a different concentration like here as a sample. Top right shows theoretical prediction. Although the spectral shape are a bit different, but the RI-dependent shift follows a similar trend. The bottom graph shows resonance angle or theta SPR with respect to sample RI. We confirm the good linear dependence between them in the experimental and theoretical prediction. And slope coefficient is almost similar to each other. So in this way, this result validates the accuracy of lambda to theta mapping OFC for SPR sensing. Next, we perform the dual cone spectroscopy of angular SPR with a lambda to theta mapping OFC. Sample is a pure water. Red plot shows the reflectance spectrum with respect to the incident angle. So the SPR dip was clearly observed here. Conversely, the green plot shows the optical phase spectrum with respect to the incident angle. So in this case, the SPR slope appeared across the center of the SPR dip, like here. In this way, the complex amplitude spectrum of angular SPR was successfully acquired. Finally, so we demonstrate the ROI-dependent shift. We measure the ROI-dependent shift of SPR dip and slope, and their ROI-dependent shift with this lambda to theta mapping OFC. Top left shows the reflectance spectrum of the with respect to the incident angle. Although we confirm the ROI-dependent shift of SPR dip, but the depth of SPR dip and their spectral shape shows some variation. The bottom left shows theta SPR with respect to the sample R indicated by red plot. We confirm the linear relationship between them, but there are some scattering like here. Conversely, the top right shows the optical phase spectrum with respect to the incident angle. So the phase slope appeared and ROI-dependent shift is more smoothly. And then so we calculate the phase change from the phase value at the fixed angle of 71.8 degrees. So the resulting, the red plot is extracted from this phase difference measurement calculation. So we compare with reflectance spectrum. So the phase spectrum shows a better linear relationship between them. So in this way, the ROI-dependent SPR shift was confirmed in reflectance and the phase spectra. Finally, we summarize the present talk using this slide. So we propose the OFC-based angular methodology for SPR sensing. Here, so we apply the spectral to angular mapping of the OFC to angular SPR measurement. We successfully retrieve the complex amplitude spectrum of angular SPR. So the SPR dip and the SPR slope. And then, so we confirm the RI dependence confirmed is both SPR dip and SPR slope. Importantly, our approach enables the retrieval of the complex amplitude spectrum of angular SPR, providing a deeper insight and a higher sensitivity compared to the traditional intensity-only method. Thank you for your kind attention.